A particular K meson has a quark structure anti-up strange. State the charge, strangeness, and baryon number. State your mom's strangeness. I'm just kidding. Kidding? I'm joking. I didn't mean your mom. Okay, here we go. So what you want to refer to, the reference that you're going to go to here is page 8, and it's section 7.3. Okay, so look these things up. We've done this, right? So look up the charge, right? You got an anti-up, right? And you got a strange, and they've got a particular charge, okay? And those charges are multiples of E, right? Okay, so figure that out. Up, anti-strange, right? Remember that anti-up has the negative charge of the up, right? And then look up the charge on the strange. Okay, that's in that table with the quarks, right? And then all quarks have a strangeness number of 0. The strange has a strangeness number of -1, so that's easy, right? Okay, so look it up in there. And then baryon number, well, it's a meson, so what do you think it would be? But go ahead and be a good soldier and look those up, right? Matter quarks have a positive 1/3 baryon number, and antimatter quarks have a negative 1/3. So you've got a positive 1/3 and a negative 1/3. Oh, I think that adds up to 0 because it's a meson, not a baryon. Okay, so let's see. Let's take a look at this. So the Feynman diagram shows the changes that occur during a beta minus decay, right? So remember, a neutron is up, down, down. Proton is up, down, up, right? So you can fill in this guy and this guy. So fill that in with the proper, right? Okay, and then it's a beta minus, so this guy's going to be your beta minus. Okay, and then put arrows on this, right? The time is going this way for this, right? So put arrows on this. The beta minus is going to go forward in time. The anti-electron neutrino is going to go backwards in time. Okay, and then let's see, we are going to tell what this particle is here, right? And of course, notice that there's negative charge on that branch there, so it's got to be the appropriately charged boson. Okay, that's going to be this guy, right? Okay, inserting the 4 missing particle symbols and the direction of arrows for the decay particles, right? Okay, let me make sure I've given you good directions on this. This is N16. Let's see, particle decay. I think that's it, number 4. Let's see what the internet says. Okay. Yeah. Let's see. Oh, okay. So you can either label this electron E minus or beta minus. Okay. I just wanted to make sure that I wasn't telling you something that was wrong. Okay, carbon-14 is a radioactive isotope that undergoes beta minus decay to a stable isotope of nitrogen-14. Energy is released during this decay. Explain why the mass of a carbon-14, and a nitrogen-14 nucleus are slightly different, even though they have the same nucleon number. And the reason is that it has to do with energy, right? When energy is released, you would predict that the result of this, the nitrogen-14, is less because of the energy of that, right? It's also that you've also created a beta minus, a actual electron from pure energy, right? So you're going to be less by the mass of that beta minus. You're also going to be less by the energy that's released. Okay. All right. Carbon-14 is used to estimate the age of an old dead tree. The activity of carbon, by the way, they can correspond. They can correlate the rings in dead trees with carbon-14 decay, and they've actually figured out that the amount of carbon-14 in the atmosphere, which is created by, I think it's created by energy from the sun or something like that. Follows, I think, sunspot cycles or something like that, right? There's an oscillation in that, and you can correct for carbon-14 dating, more than you needed to know, right? So explain why the activity in the dead tree decreases over time, and the answer to that is that that activity is Is it negative? I can't remember. I should really look that up. I think it is because we're losing the nuclei. Okay. I want to say that it is, but I could be wrong. Could be wrong. Oh no, they don't make it negative. It's ignore the minus. Ignore that minus sign. Right? Okay. The activity, basically, activity is the opposite of the derivative of the number of things you have. But anyway, the activity is proportional to the number of particles you have. And so as they decay, you have fewer undecayed nuclei, and so n goes down, and therefore the activity goes down, right? Okay. Calculate in years the age of the dead tree. Give your answer to an appropriate number of sig figs. Oh, how many sig figs? We should have 2, right? 2 there. There's 2 there, so our answer should have 2 sig figs. Let's make sure we do that, right? Because that's, by the way, one of the 3 marks is to give the correct sig figs, right? Okay, so we're going to use n equals n naught e to the minus lambda t, right? Okay, so here they're given the half-life, right? So our decay probability is ln2 divided by 5,700 years. Right. Now notice that this is going to be, and that's going to have the units of years to the minus 1. Okay. So lambda will be something years to the minus 1. So that means when we calculate time, time will be in years, which is exactly what we want, right? Okay. Okay, so let's see. So then what you're going to do is you're going to plug in, they say that the activity has fallen to 21%, right? Okay, so what we're going to do is we're going to say that it's 0.21 times the original activity, right, is equal to the original activity e to the minus lambda t, right? And I could, I don't know. It's just basically anything that scales with the number of atoms you have, you can use this formula on, right? So ultimately what happens is we end up with 0.21 equals e to the minus lambda t. Now we have lambda here from this. You're going to plug that in. You're going to solve for it and get something like 12,833.8 years, and then round that to 2 sig figs, okay? Do your maths.